that you had for homework today. So the first question, it asks you to define electronegativity. Well, that's a definition that comes up an awful lot. It's the relative attraction that an atom in a molecule has for the shared pair of electrons in a covalent bond. Then they asked you to draw dot and cross diagrams to show the bonding in those molecules there. Now you need to look for nitrogen in the periodic table. It's in group 5. So 1, 2, 3, 4, 5 electrons in the outer shell of nitrogen. When you look up fluorine in the periodic table, it's in group 7. Now remember that if you dot nitrogen's electrons, you have to cross fluorine's electrons. So X there, fluorine. Now fluorine's in group 7, so you have to draw 7 electrons in the outer shell of fluorine. 1, 2, 3, 4, 5, 6, 7, and 1, 2, 3, 4, 5, 6, 7. So that's dot and cross diagram there for that. Boron trichloride. Boron is in group 3. So boron has 1, 2, 3. And again, you're going to have to draw 3 fluorines. And remember that fluorine is in group 7. So you have to draw 7 electrons around the outer shells of the fluorines like so. Okay. And then lastly, they ask you to draw CLF. I'll draw that in 1 second. But before I do, look, in the second part of that, they said, use electron pair repulsion theory to predict the shape of boron trifluoride. Well, boron trifluoride here has 3 bond pairs of electrons. So 1, 2, 3. So that's trigonal planar or trigonal planar, whichever word you want to use there. Okay. Now, CLF, then they also asked you. So chlorine is in group 7. 1, 2, 3, 4, 5, 6, 7. Fluorine, we'll dot fluorine's electrons this time, because remember you have to dot one set of electrons and X the other. So that's the dot and cross diagram. Now in the last part they ask you to use electronegativity values to indicate on your bonding diagram for the fluorine monochloride any partial charges that you would expect. Now when you look up electronegativity values for fluorine, fluorine is 4, and when you look up chlorine, you'll find that chlorine is 3.16. So 3.16, and it's not quite 4, actually, it's 3.98. Now, the difference when you subtract there is 0.82. So when they ask you to indicate in your bonding, you're going to have to say that the fluorine is slightly negative and that the chlorine is slightly positive. So that fluorine, so if we kind of rewrite our electron pair there, that fluorine atom is getting a greater share of the electrons. Because it's more electronegative, it's pulling the electron pair closer to it, making it slightly negative. And then finally in question 1, they ask you to predict the type of bonding in chlorine monochloride. Well, because the difference in electronegativity is greater than 0.4, we're going to say that the bonding is polar covalent, okay? Because it's greater than 0.4 but less than 1.7. All right, so that's question 1. Question 2, then they ask you to identify in ammonia the type, so ammonia is NH3, the type of intramolecular bonding. Now remember that intramolecular bonds are bonds that hold the atoms together within the molecule. So you have 3 bonds there holding the nitrogen to the hydrogen atoms in the molecule. And because, again, if you look up the difference in electronegativity there, you'll see that hydrogen is 2.2 and nitrogen, when you look up the electronegativity value for nitrogen, you'll find that it's 3.04. Okay, so the difference there means that it's polar covalent bonding. Okay, polar covalent bonding. So covalent bonding, polar covalent bonding. Okay, now what kind of intermolecular forces? Well, look, what did you notice? You notice that nitrogen is bonded to hydrogen. The other examples is where you have hydrogen bonded to fluorine or oxygen. So phone, remember phone? So hydrogen bonding are your type of Remember, intermolecular forces are forces that hold atoms, or forces that occur between one molecule and the next. So just to recap there now, the intramolecular bonds would be polar covalent. The intermolecular bonds would be hydrogen bonds. Okay. Question 3 asks you to account for the difference in shape between boron trifluoride and ammonia. Now we drew out boron trifluoride in question 1. It's triangular planar or trigonal planar. But you've got a lone pair of electrons here now in the ammonia. Look. And what's that lone pair going to be able to do? It's going to be able to push or repel the bond pairs closer together. So this is triangular planar, yeah, but this is pyramidal. So they both have three bond pairs of electrons, but because of the lone pair of electrons there in ammonia, then you make the shape different. The shape is pyramidal, 3 bond pairs in 1 lone pair. Question 4, then again, same definition of electronegativity. And then it says, again, they're using the example of ammonia, and then they're using silicane. They have 4 pairs of electrons, it says, around their central atom, but they want you to account for the difference in the shape. Now, when you draw it out, look, okay, you're going to see there again that whereas silicane is in group 4, look, so that's going to be the bonding there, okay? So this one is tetrahedral. It does have 4 pairs of electrons, 1, 2, 3, 4, and this one has 1, 2, 3, 4 pairs of electrons as well. But because these are lone pairs of electrons, then what are those lone pairs going to do? They're going to push the bond pairs closer together. So that closes in that angle to 107.3, whereas this angle between the bonds here, you have 109.5. Okay, so that's the difference, the lone pair there. Now it says use electronegativity values then to determine which bond is more polar, okay? So when you look up the values, you're going to get nitrogen is 3.04, hydrogen is 2.2, silicon is 1.9, and hydrogen is 2.2. The difference there is 0.84. The difference between these two is 0.3. So clearly, this bond here is going to be more polar, which is what they asked you to do. And then which of the two substances has a hydrogen bonding between its molecules? Well, the ammonia. Why does ammonia have hydrogen bonding between the molecules? Because hydrogen is bonded to nitrogen. Remember, the other two possibilities would be fluorine and oxygen. So where there's hydrogen bonded to nitrogen, you can have hydrogen bonding. There is no hydrogen bonded to either fluorine, oxygen or nitrogen here, so not hydrogen bonding. And to give a reason, or the reason why a molecule with polar bonds can be non-polar. Now, this can be difficult enough to understand. Sometimes you might have a molecule that has polar bonds, okay? So say, for instance, carbon tetrachloride. Here's carbon tetrachloride. Now, when I put in the charges, then here are the charges, right? Now, there are polar bonds in that molecule. That's a polar bond, that's a polar bond, that's a polar bond, and that's a polar bond. But lads, when you look and see where, if you want to figure out, is this molecule polar overall? Is it polar overall? You need to look and ask yourself, well, where is the centre of positive charge and where is the centre of negative charge? This molecule is symmetrical. Imagine your tetrahedral shape. The centre of positive charge is here, where the carbon atom is. Where is the centre of negative charge? Well, you can fold, look, that up. And where is your centre of negative charge? In here as well. And if the centre of positive and the centre of negative charge is in the same place, then your molecule is not polar, okay, even though it might have polar bonds. Another example would be something like carbon dioxide, okay, slightly positive, slightly negative. This molecule does have polar bonds, okay, that's a polar bond and that's a polar bond, but when you ask yourself, is the molecule overall polar? Where is the centre of negative or positive charge? Here at the carbon. Where is the centre of negative charge? Here at the carbon, because it folds up on top. It folds in on top of the carbon. So it's a symmetrical molecule. So the simple answer is, if the molecule is symmetrical, then even if there are polar bonds, the molecule overall is not polar, non-polar. So you're looking to see if the positive and the negative charge is in the same place, the centre of positive and the centre of negative charge is in the same place, then it's not polar, even though there might be polar bonds within the molecule. So you're looking for tetrahedral molecules, okay, and you're looking for something like triangular planar molecules. They would be symmetrical, not something like HCl. Look, the centre of positive charge is here, the centre of negative charge is here. So that's polar molecule. All right, so that can be kind of difficult at times, but that's your answer. So give a reason why the molecule with polar bonds can be non-polar. You're going to say that the centre of positive and the centre of negative charge is in the same place. And even though then the molecule has individual polar bonds, it's not polar overall. How many sigma and pi bonds results from nitrogen? Well, you know nitrogen's in group 5, so 1, 2, 3, 4, 5. And 1, 2, 3, 4, 5. So nitrogen has triple bonds there to satisfy the valency of each nitrogen atom. So what's a triple bond? A triple bond is 1 sigma and 2 pi. So you need to say 1 sigma bond and 2 pi bonds. Question 6 asks you to distinguish between intra and intermolecular bonds. So intramolecular forces are forces that hold atoms together within a molecule, and intermolecular are forces between. Remember all the E's, between one molecule and the next. And then they ask you to explain why the boiling point of hydrogen is significantly lower than the boiling point of oxygen, okay? Now, these are obviously both non-polar molecules because there's no difference in electronegativity between the atoms. So you're going to have to say that hydrogen is a smaller molecule, okay? So it's a smaller molecule, right? There are less electrons in the hydrogen molecule, and therefore if there are less electrons, then it's going to have a weaker van der Waals forces because they have weaker temporary dipoles. So weaker temporary dipoles, so weaker van der Waals forces. Or alternatively, you could of course take it from oxygen's point of view and you could say oxygen has more electrons, therefore oxygen will be able to set up stronger temporary dipoles and as a result have stronger van der Waals forces, and therefore it would need more energy to break the van der Waals between oxygen molecules, resulting in it having a higher boiling point. Iodine is very low solubility in water. Again, iodine is a non-polar solute. It will not dissolve in a polar solvent like water, okay? No, won't dissolve in a polar solvent like water, will dissolve in a non-polar solvent, something like cyclohexane. And remember our sentence for solubility, like dissolves like. So a non-polar substance will dissolve in a non-polar solvent. A polar substance will dissolve in a polar solvent, like dissolves like. And finally then it says, if you have water in a burette or something and you bring a positively charged rod or any sort of charge, I'm saying it's positively charged rod, you're going to say that the water is attracted towards the rod. How would you explain that? Well, water is polar, okay? So you have the H2Os, you have slightly negatives, so it's the slightly negative oxygens that will attract to the positive rod. If it was a negatively charged rod that you had, then it would be the positive hydrogens that would attract. So either way, regardless of the charge on the rod, the water is going to be attracted towards the rod, okay? And then finally, Q-X for possible shapes. Well, 4 bond pairs, because you can see the 4 there next to the X. So you're going to say tetrahedral, aren't you? Sorry, I didn't draw that very well there now. So for Q-X4, yeah, 1, 2, 3, 4, tetrahedral is your possible shape. And the bond angle is 109.5. Thank you.